So this one, yeah, copy from backwards from the next cell. Yeah. We can open that to.
Okay, cool. Cheers. Okay, hi everyone, I'm Joe, and today I'm going to be talking about some work we've been doing on high-order structure preserving schemes on GPU architectures in FEniCSx. This is some work I've been doing with Igor and Chris and Garth. It's very much a work in progress, and that means that my talk today suffers from the unfortunate problem of not really having any results in it. So I apologize in advance for that. The other problem is that I'm going to start by talking about the magnetohydrodynamics equation because that's the target application, but most of what we've done so far has been in relation to Poisson's problem. Okay, so the magnetohydrodynamics equations describe the motion of conductive fluids in electromagnetic fields, and they're made up of the incompressible Navier-Stokes equations and a simplified version of Maxwell's equations. And they're coupled because the fluid experiences a Lorentz force as it moves through the electromagnetic field. And also a current is induced within it due to this U cross B term that appears. And these equations have some applications in things like nuclear fusion, etc. Now, these equations have an incredibly rich structure to them. And one way to kind of see this, if we just focus on Maxwell's equations for now, is that if you think about, is that different electromagnetic quantities appear to be associated with geometric entities. So for instance, the magnetic field, the H field, is in a sense associated with lines. It's the circulation of the H field around lines that's the magnetomotive force, for instance. Similarly, with the magnetic induction, the B field is associated with surfaces. It's the flux of the B field that appears through surfaces that appears in Faraday's law. And the H field has always continuous tangential components, but sometimes the normal components jump. And the reverse is true for the B field. And with the H field, we usually take its curl, whereas with the B field, it's the divergence operator that acts. So all of this structure is encoded really neatly in this diagram, which I absolutely love. It's from Bozowitz's book on computational electromagnetism. And each layer is connected by the de Rham complex. The front and back layers are connected by the time derivative, and the left and right layers are connected by constitutive laws. And you can essentially read all of the fundamental laws of electromagnetism off the diagram. So the idea was, and it turns out the structure within this diagram is really important for the well-posedness of problems within electromagnetism. Now, the idea with structure preserving methods is that you replace these infinite dimensional Hilbert spaces with finite element spaces that replicate this structure at the discrete level. And then you effectively automatically inherit these stability properties in the discretization. And you often also get nice things, nice conservation properties too. So in the context of electromagnetism, you can get schemes that have exactly solenoidal B fields. In the context of fluid mechanics, you can have exact mass conservation. Okay, so we have these cool schemes. Let's solve some interesting problems on HPC systems. So many codes are designed to run on CPU architectures, but with the drive towards the X scale, power efficiency is becoming really important. And also because of AI, we're finding that modern architecture is heterogeneous and contains GPUs, which have the potential to do a lot more work per unit of energy than CPUs. Now, GPUs achieve performance through parallelism. You execute a task on many, many thousands of threads. And so it's important to keep these threads busy. In other words, you need to use algorithms that have enough arithmetic intensity so that you're not just sitting around waiting for data all the time. And the problem is that a lot of codes, low-order matrix-based codes, rely on operations that don't suit this architecture well. And so one thing we've been doing in Phoenix is to implement some algorithms that do. I should say at this point, I'm pretty new to this. I've only been working on this for a couple of months, and most of the work that exists already has been done by Igor and Chris. And there's kind of three key components to this: high-order elements, matrix-3 methods, and p-multigrid. Okay, so let's start with high-order elements. Okay, so high-order elements, not only do you get high-order accuracy, at least for smooth problems, but you also end up with increased arithmetic intensity, which is really important for this kind of architecture. Now, the problem, though, is that a naive implementation results in high algorithmic complexity and also a lot of data because the tables for these basis functions, there's a lot of degrees of freedom, so you end up with large tables. At the moment, FFCX writes all this into the kernel, which is not really well suited for GPUs. So a well-known solution to this problem is to use something called sum factorization, which is where you start with the element in 1D, And then you kind of exploit the tensor product structure of tensor product cells to combine two of the intervals together into a quadrilateral element. And then once you have that, you take that quadrilateral element, take its tensor product with another 1D element, and you get the hexahedral element. And the nice thing about this is that you reduce the algorithmic complexity, and also you only have to store the tables in 1D, which means there's a lot less to store. Now, thanks to some work that Igor's done, this is possible in FFCX. You just add this sum factorization flag. However, unfortunately, at the moment, it's limited to Lagrange elements. So if we try to run this on magnetohydrodynamics.py, it's not going to work. And this is something I'm going to try and look at soon. As a kind of an aside, with higher elements, you want to use high-order geometry. And it turns out that the accuracy of tensor product HDiv and HCurl elements significantly degrades when we have non-affine maps. I'm not really sure what a good solution to this is, so if anyone has any thoughts, please let me know. Okay, so the next component is matrix-free operators. So traditional finite element codes work by looping over the elements in a mesh, assembling or computing the element contribution, and then assembling that into a global system. And then once you have this global system, you might solve it, say, using an iterative method, which involves lots of sparse matrix vector products. And the problem is these operations have low arithmetic intensity and aren't really well designed for modern architecture. And this means that you actually saturate the memory bandwidth of modern GPUs at less than a percent or two of the peak peak floating point throughput. So one solution to this that reduces memory bandwidth is to rely on matrix-free operators. And this works because iterative solvers don't actually need the assembled matrix. It's a bit tricky with preconditioners, but let's gloss over that for now. You just need to know the action of the matrix, how it acts on vectors. It's actually really easy to get a matrix-free kernel in Phoenix. You just start with your form, add a coefficient, and then wrap the bilinear form in this action thing, which just replaces the trial function. The problem is that the kernel that it computes, that it compiles, is kind of really designed for CPUs. It's not really well suited for GPU architecture. And so what we're actually doing at the moment is start using that as a starting point and then effectively hand modifying the kernel so that each thread block on the GPU works on a cell and each thread works on a degree of freedom. Okay, so we have these high-order matrix-free operators with some factorization that we want to use. The question is now, how do we actually solve the system? A natural choice is to use multigrid methods, but things like algebraic multigrid don't converge slowly for high-order methods. So a natural choice in this context is to use p-multigrid. Now, the way p-multigrid works is pretty much the same as standard multigrid methods. You start from a mesh, you have your high-order function space defined over it. These are the degrees of freedom. And then what you do is you construct a hierarchy of levels. In normal multigrid, this is done by coarsening the mesh. In p-multigrid, what you do is you change the polynomial degree. So here we're going from P4 to P2 to P1. The rest is pretty much the same. You iterate, we're using Chebyshev smoothers on each level, and on the coarse grid, we are solving using algebraic multigrid, and then transferring the correction back up the levels. To implement the prolongation operators in Phoenix, we're making some use of some work that I think Matthew and Jürgen did, which allows interpolation between arbitrary finite element spaces. And then to restrict the residual, we're using the dual of this operator. Okay, so just to summarize, traditional methods aren't particularly well suited for modern HPC architecture. And so we're using FEniCSx to implement some high-order kernels and matrix-free operators and p-multigrid for GPUs. Currently, this involves a lot of modification by hand, but the kind of long-term goal would be to code generate for GPUs. And again, most of what we've done so far is really focused on Poisson's problem, but the aim is to extend these techniques to magnetohydrodynamics. This means things like more advanced smoothers for the p-multigrid and a handful of other things. If you want to check out the code, it is open source and available. However, like I say, it's a work in progress, a bit rough around the edges, and not everything works yet. So there's still a lot to do. Thanks for listening. Are there any questions?